All right, so today we'll try to focus on one particular type of neural network, which is multi-layer perceptrons. Um, with some modifications, you can apply what we do today to other types, for example, radial basis functions as well. But MLP is probably one of the simplest structures of neural networks, so it's more appropriate for our starting point. Let's have a quick recap of the things that we have talked about before. So as we saw, a multi-layer perceptron is a neural network that has three layers: input layer, hidden layer, and output layer. Input and output layers are not anything special. They basically like linear functions. They receive an input or a sum of some signals, and they add them together, pass it along to the next node. The special neurons in an MLP would be the neurons in the hidden layer. These are neurons that have an activation function. And as we discussed, these activation functions are commonly either sigmoid function or hyperbolic tangent. What happens is you have your input layer, and then you provide your input to the network. You have an input weight matrix W and output weight matrix V. W represents the coefficients that the weight coefficients that are between the input layer neurons and the hidden layer neurons. And then V matrix represents the weight coefficients for edges that connect the hidden layer neurons to output layer. When we talk about designing a neural network, you would essentially have to decide on three things: the number of neurons in the hidden layer, the weight coefficients for the input side W, and the weight coefficients for the output side V. So once we know these three sets of parameters, we basically know what the neural network is and what structure it has. To have a quick overview of the things we have already talked about, essentially we saw that the activation signal for every particular neuron in the hidden layer would be the summation of all the inputs. So imagine your input is m dimensional, has m different features. So all those features multiplied by the corresponding weight coefficients, wji, which would connect input I to neuron j. Once we have these activation functions, this is what is applied to the neuron in the hidden layer. And then based on what type of activation function we have, the neuron will generate some signal which we call a decision signal. So for that neuron J, decision signal D is going to be a function of the activation signal, and this function phi is basically what I mentioned would be a sigmoid function or hyperbolic tangent. Once we know all the decision signals of individual neurons in the hidden layer, these are going to be weighed based on the weight coefficient V's and then added together to generate the output y hat of k. So y hat of k will be the summation of all the outputs of individual neurons multiplied by the weights that connect them to that particular output neuron. This is what we call the feed-forward path. This is where you apply the input to the neural network, and then it kind of works its way towards the output, which is your estimated output of y hat. Sometimes, in addition to the usual inputs, the usual dimensions of the input, we want to add another constant as an additional input. This is what we call a bias input. Bias sometimes helps us with adjusting the weight values of neurons and the input weights and output weights more effectively. And in fact, in the example that we're going to do later today, I would like you to add this bias input as well. Essentially, what this does is it increases the dimension of your input by just one dimension. And that particular dimension is going to be the constant of 1 at all times. So it's not a value that changes. If you have an input signal which is 3-dimensional, with this added bias inputs, you will now have a 4-dimensional input space in which one of the dimensions is basically like a constant 1. Once we have done the feed-forward path, we will move to the backpropagation path. This is the path we do for updating the weights of the neural network, which is essentially what we mean when we say we are training the neural network. The first step would be to form an error signal. So the error signal for any particular neuron would be the actual output corresponding to that input minus the estimated output that is provided by the neural network. So for that particular set of input dimensions and features that have been applied to the neural network, we know during training that the output should be y of k, but our neural network, because it's not ideal, it will generate some other output, which is y hat of k. The difference between the two, and pay attention, it's y minus y hat. The difference between the two would be the error signal for that particular neuron. If you have 5 different neurons in the output layer, your error signal is going to be 5-dimensional, one error signal corresponding to each output neuron. Once we know the error signal, we can then go ahead and update the input and the output weights. The easier one would be the output weights, VKJs. Again, VKJ is the weight coefficient for the edge that connects neuron J in the hidden layer to neuron K in the output layer. VKJ for the next time step will be what I have right now plus eta, which is my learning rate parameter, times the error for that particular neuron times the decision signal for that neuron in the hidden layer. And again, as we talked about it last week, eta, which is your learning rate parameter, is typically a number between 0.05 and 0.1. You can use smaller values, you can use larger values, but heuristically speaking, this range of 0.01 to 0.5 has been shown to be more effective. For input layer weights, the equation for weight update is a little bit more complicated. So WJIs, and WJI is the weight coefficient corresponding to the edge that connects neuron I in the input layer to neuron J in the hidden layer. WJT plus 1 will be what I have right now, plus eta, which is my learning rate parameter, times this term, which is a series of multiplications based on the error signal, based on the output weight parameter, based on the input signals, as well as this term that you see here. This term that you see here, the partial derivative of the decision signal of neuron J with respect to its activation signal, it's essentially the derivative of the activation function that you have chosen. If you have a sigmoid function, this partial derivative is going to be d of j times 1 minus d of j. And if you have chosen hyperbolic tangent, the partial derivative is going to be 1 plus d of j times 1 minus d of j. Now, these are basically kind of complicated looking partial differential equations, or partial derivative rather, equations that might be a little bit daunting. In practice, however, when we try to model neural network in Matlab or any other software for that matter, and train it, we often go with much simpler matrix equations. And typically what you have is a series of equations that again would mimic the feed-forward path as well as the backpropagation path. I'm going to show you these sets of equations, and when we're done with the lecture and I want you to start coding this yourselves, I'm going to bring this slide back again just so you can look at it and follow my suggestion in terms of the matrix calculations, because like I said, this is a lot easier than the equations that I showed you on the previous 2 slides. So imagine that my output signal is one-dimensional. I'm just making this assumption for kind of demonstration purposes. It doesn't have to be, but when the output is one-dimensional, meaning that your neural network is just estimating one particular signal, is not a multi-dimensional output. When that's the case, it's easier to implement. So we're going to start it like that. But if you're interested in knowing how to deal with higher dimensional output signals, it's not really much different. I mean, we just have to update the dimensions of matrices. So typically for neural network training, the first step for us would be the initialization of the network. By initialization, I mean we would have to decide on the number of neurons in the hidden layer. So this parameter is something that you have to decide on. number of neurons in the hidden layer. And then once you have that, you know that W will be a matrix of the dimensions, number of neurons times 2. Remember that W is a matrix that goes from the input space to the neurons in the hidden layer space. In the hidden layer, we have number, but let's call this for now N. It's a little bit simpler to keep saying N rather than number of neurons. So this is going to be a 2 by N matrix. And the reason why I have 2 is I'm looking at a neural network that will receive an input X, one-dimensional, and will generate an output Y, again, one-dimensional. However, because I have that additional input, which is the bias of constant 1, my input space now will be 2-dimensional. One of them, of course, will be variable as X varies. The other one will always be constant. It's just a constant input. So my W matrix is going to be N by 2 because it converts the signals from a 2-dimensional space to an N-dimensional space. And then V is going to be 1 by N because it converts the signals from an N-dimensional space corresponding to neurons in the hidden layer to a 1-dimensional space, which is going to be your output. So that's the size of the W and V matrices. We first have to randomize them. So in Matlab, when you use the rand function, essentially it randomly allocates values between -1 and 1, which is what we want. I'm sorry, between 0 and 1, which is what we want. Then we have the feed-forward path. In feed-forward path, I'm basically converting everything I showed you in the previous slides into matrix calculation. So my activation function will be a vector that will come from multiplication of the W matrix times X. Remember that X in this particular case is 2 by 1 and W is N by 2, meaning that my activation function is N by 1, one entry per neuron in the hidden layer. Decision function, I have chosen hyperbolic tangents. My experience tells me that this is a more diverse function than sigmoid, but sigmoid works the same way. It works perfectly fine as well. So you can choose either one you want. They don't have like fundamental differences. The only difference would be that the weight values with one would most likely be mostly positive, with the other one would be positive and negative, which is just an observation on the weight coefficients and nothing structural about the behavior of the neuron. So this will be the decision function, and then y hat, I define a structure for my y, which is the actual value and the estimated value. Y hat is again matrix V times decision function. And again, remember that decision function is N by 1 and V is 1 by N, meaning that my estimated output Y hat will be like a scalar, a 1 by 1 value. This is my feed-forward path, and then I will go through the backpropagation path. In backpropagation path, I first define the error, which is going to be the actual value of Y minus the estimated value. Again, remember that for every corresponding to each X value, you should know what the actual value of Y is, because this is supervised training. By knowing this value, you can form an error, and then you use the error to update the weights. The rather complicated equations for weight update that I showed you on the previous slide can actually be written in a very simple way in Matlab. So your vector V will be updated as follows. The new V is going to be the old V times eta, which is your learning rate parameter that you have to choose, times error, which is 1 by 1, times decision function. Notice that decision function transpose, because decision function is N by 1, and I have a V which is 1 by N, so I have to change it to, I have to transpose it to decision function is 1 by N as well. W is going to be W plus eta, learning rate parameter, times error, times V transpose, times 1 minus decision function. Notice that this is not the regular multiplication. This dot multiplication in Matlab is essentially a point-by-point multiplication. That means it takes two vectors or two matrices of the same size and length, and then multiplies the corresponding entries by one another. So this is a kind of a dot star 1 minus decision function. Again, dot star 1 plus decision function times x transpose, which is my input vector. And again, remember that 1 minus decision function times 1 plus decision function, that's the partial derivative of hyperbolic tangent. If we had the sigmoid function, this would have been decision function times 1 minus decision function. So this is basically what we have. Now, before I show you a sample code, I would like to discuss the problem that we're trying to solve today. This, in fact, is the problem through which I learned neural networks myself when I was a grad student. It's a very simple problem, and it's something that all of us can do in less than an hour. So what I would like to do is I would like to design an MLP neural network that models a nonlinear system with this dynamics: y equals 2x squared plus 1. I am assuming that x changes between -1 and 1. I would like you to design this neural network, provide the mean squared error as a performance metric for your neural network, and provide also testing results. Basically test the performance when you have stopped training the weights of the neural network and just applying individual inputs, and see how well the neural network is performing. We're going to do this for two sets of inputs. One is that inputs that go between -1 and 1, for which the neural network has been trained, and then inputs that change from -2 and 2. Part of this input space the network hasn't seen before, hasn't been trained for. So we would like to see how the network behaves. So before I show you the code, let's walk through the different steps that we have to perform. Step 1 would be we have to initialize matrices W and V. These have to be random matrices. You can basically have them between 0 and 1, or you can have them between -1 and +1. It doesn't really matter. It's just a design choice rather. In step 2, you will basically iterate a feed forward and back propagation loop. What does that mean? You randomly choose one x value. For that x value, you go through the feed forward path, basically calculate the estimated output of the neural network, then do the back propagation by comparing that estimated value with the actual value that is supposed to be, forming an error signal, going through in the reverse direction, updating the weight parameters, and then this will be one iteration. Then you continue these iterations. Every iteration is going to be a training sample. You do this for a couple thousand number of samples, and then once you feel comfortable, you stop the training. When we say you stop the training, that means you're not updating the weights anymore. Now, with whatever weights you had before, you will basically apply values, x values from -1 to 1, perform the feed forward path, calculate the actual y and the estimated y, and typically plot them on a graph. And again, notice that here we don't have a back propagation path. So let me now show you the code that I have written for this purpose. So as I mentioned, I'm not going to share this with you because I don't want you to copy my code necessarily. I'm just showing it to you so you get some sort of an idea of how this should look like. So essentially, first you start with some parameters. And here I have chosen 10,000 samples. My learning rate, I have chosen it to be 0.05. I encourage you to play with different numbers to see what difference it makes. And the number of neurons in the hidden layer, I have chosen it to be 6. Next step, once I have these parameters, I initialize my matrices. So W, as I mentioned before, would be an n by 2 matrix in this particular case, because remember that I have two inputs. One is x, the other one is the constant bias of 1. And then output is just single dimensional, is just a y. So my W is a random matrix. I'm using the function rand of n by 2. And then V is a random matrix of 1 by n. Sum of errors is just an auxiliary variable that I define because I want to be able to define my mean squared error later. So let's start with this. So now this is the training process. I go through this loop for as many number of steps as I have defined in number of samples. So in number of samples, I have 10,000 samples. That means I provide 10,000 samples to my neural network, and for each sample, I go through feed-forward and backpropagation. Feed-forward path, I basically would like my inputs to be randomly chosen. And remember, I wanted the values of x to be between -1 and 1. Rand function in Matlab gives you values between 0 and 1. So if you want to change it to +1 and -1, you would basically multiply it by 2 and then subtract 1. So my x, which is a 2 by 1 vector, its first entry would be 2 times some random value -1. There is a guarantee that this is going to be between -1 and 1. And then the constant one. This is my bias input. Activation function is my w times x. Decision function, I'm using the hyperbolic tangent function of the activation function. And y hat is simply going to be matrix V times the decision function. That takes care of my feed-forward path. Now in my backpropagation path, I would have to calculate the actual value first. Well, if I know the actual x, which in this case would be the first entry of my x vector. So if I know my x, because the dynamics I'm trying to learn is 2x squared plus 1, my actual value will be 2 times that x value squared plus 1. And then error will be the actual value minus the estimated value that comes from the feed-forward path. And then the basically weight update equations that I showed you earlier, my v is going to be the old v plus eta plus the error signal times the decision function transpose, and w is the old w plus the learning rate parameter times the error signal times the output vector, weight matrix rather, and transpose. Notice that again, this is a dot multiplication, 1 minus decision function, dot multiplication, 1 plus decision function times x transpose. Then what I do is at any point in time, any new error value that I get, I calculate the 0.5 times error squared, because the summation of 1/2 of the summation of all the errors squared, that would be the sum of error that I have. So I will have sum of error, which is the previous value. Notice that I initialize this as 0, but as the loop continues, this will be updated at every step. Plus 0.5 times error squared. And then what I would like to plot is basically the number of steps, which is the same as the training samples that I have, and as well as the MSE, the mean squared error. The mean squared error is going to be the sum of error divided by the number of steps. So as you continue moving towards the end of your training cycle, obviously the sum of error increases because you keep adding additional errors to it. But by dividing it by the number of steps at that particular point, you're basically making sure that that value goes down. For testing purposes, this is quite simple. Here, notice that in the previous case, when I had my or rather during the training stage, I would randomly assign x values because I don't want my neural network to learn a pattern. I don't want to say to my neural network that, hey, x always goes from -1 to 1. I don't want the network to learn this unnecessary dynamic. I want the network to know that x could be anywhere from -1 to 1. When you're testing, however, this is not necessary anymore because your network is not being trained, meaning that it is not learning any particular dynamics. So my test input is going to be moving from -1 to +1 in steps of 0.001. At every time step, I have a counter that I basically increase that. My x is going to be the test input, which is my x value, as well as the 1, which is my constant bias. Activation function is w times x. Decision function is hyperbolic tangent of the activation function. The estimated output is just v times decision function. The actual output is 2 times that particular x value plus 1. and then I will plot these together. Let me run this code for you so you see how it's going to look like. So remember that this is 10,000 samples with 6 neurons in the hidden layer. So when I run, and it takes about a few seconds to kind of converge. So in this case, about 3 seconds. And this is the graph that I'm looking at. So let me, for some reason, this is not, oh yeah. So in the plot in the right-hand side, I have my real and estimated output. Notice that here, my blue line is the estimated output, 2x squared plus 1, and the red line is the real output. And you can see that there's a very good matching between what the neural network has learned. On the left side, I have the mean squared error. This is, again, remember, the summation of all the errors divided by any particular, by that iteration time step at that particular point in time. And essentially what you expect to see is that as you add more and more errors together, of course, the sum of errors would go up. However, because you're dividing it by the number of iterations, collectively, this should go down, as you can see here. So this basically tells me that 10,000 iteration samples is good. Maybe I would need more, because notice that this error surface hasn't flattened yet. So maybe it's an indication that if I increase training samples by another 20,000 samples or 10,000 samples, maybe the error will go even lower than that. But if I had stopped, for example, at 4,000, maybe my network would not have had a good performance as it has now. So let's do that test. And this is something that I would like you to do yourself later when you write this code. But just to show you, imagine I go with 4,000 samples instead of 10,000 samples. And notice that with 4,000 samples, my network hasn't really learned much. So that indicates that there's a lot of dynamics that is not sufficient in 4,000 samples for the neural network. Instead, if I make it, for example, 20,000 samples, I can get a better performance. Notice that here, my error is, going further down. Other tests that you can do, for example, would be playing with the number of neurons to see what difference that would make. And again, we have discussed this in our lecture last week, that if you have too few neurons, that is not going to be sufficient to learn the dynamics. If you have too many neurons, it's not sufficient to learn. Too many neurons, it would actually overfit your data. So there is a kind of a sweet spot in between that is often needs to be determined by trial and error. The last thing to show you before we open for questions and then I let you do the code yourself is, remember that I trained my network for x values between -1 and 1. So I would expect that if I test it for x values between -2 and 2, for values it hasn't seen, most likely it's not going to have a good performance. Let's see that in practice. This shows that to you completely. So this network has performed very well for values between -1 and 1. And notice in testing purposes, this is -1 and this is +1. So if x values are between -1 and 1, my neural network is actually, the blue line, is following it very closely. But if I extend this beyond the values for which the network has been trained, the network is hopeless. It's not anywhere close to where it should be. That's an indication that if you have not presented a particular data set to your neural network, you cannot expect the network to know how to follow that.